we are going to define a new concept as enthalpy. So this is the first part. We're going through the definition, and then we are going to start thermochemical equations that are included enthalpy. So we have to know enthalpy first, and then we go through the thermochemical equations. So what is enthalpy? Enthalpy is the heat evolved in a chemical reaction at constant pressure. And that's how it is defined mathematically. It's the internal energy plus PV, pressure and volume. So enthalpy, we show enthalpy with H, and as you see, it's a capital H, which shows it's a state function. But just like the internal energy, it's impossible to determine the exact amount of enthalpy of a substance, but we can measure the change in enthalpy. So we can find delta H. And just like any other state function, delta H is defined as final state minus the initial state. Therefore, delta H is the enthalpy of the final state minus the enthalpy of the initial state. So as I said, we cannot measure the amount of enthalpy of one state, one substance, but we can find the change. So although we define it as H final minus H initial, we cannot find the amount of enthalpy of that state, but with some methods we can measure the change in enthalpy as delta H, and we're going to learn how to do that. For a chemical reaction, we define delta H, the change in enthalpy, by the enthalpy of the H of the product minus the H of the reactant. If you think about it, delta H is H final minus H initial, right? So when you have a chemical reaction, the initial state is when we have the reactant, the final state is when we have the products. Okay, so H final is the enthalpy of the products, and the initial H, H initial, is the enthalpy of the reactants. So delta H for a reaction is the H of products minus the H of the reactants. And this figure is how basically what happens in a chemical reaction, right? So if you think about mixing of hydrogen and oxygen and forming water, okay? So when hydrogen and oxygen are mixed together, there is a release of heat and water is made, okay? So water has lower enthalpy, okay, lower energy. So this kind of reaction is called exothermic reaction. So exothermic reaction. In exothermic reaction, since this is the energy diagram, right? So water has lower energy than hydrogen and oxygen. So if we have H final, which is H of reactants, minus H of H of product minus H of reactants. So if you have lower value minus a higher value, what would be the sign of delta H? It will be lower value minus higher value, so you get a negative delta H. But in some reactions, we absorb the heat from the surrounding and to do the reaction. Like for example, this reaction B, HGO absorb the heat by the system, and the system is the reaction, right? Absorb the heat from the surrounding, and then it makes these products. Okay, so in this case, these are reactant. This is reactant, and these are products. In the first reaction, these two were reactants, and water is the product. Okay, so in the second reaction, the reaction absorb heat. So these kind of reaction are called endothermic because they require heat. If they give off heat, that's exothermic. If they absorb heat, that's endothermic. Okay, so this is an example of endothermic reaction. In an endothermic reaction, the product have higher energy, higher enthalpy. Okay, so and you know delta H is H of product minus H of reactants. So if you subtract H, if you have H of product, a higher value, minus H of reactant, a lower value, therefore your delta H will be a positive number, right? So for exothermic reactions, the reactions that gives off heat, the enthalpy is a negative number. For endothermic reaction, the reaction that require heat for the reaction to occur, we have delta H as a positive number. Okay, so now that we know what is exothermic and what is endothermic reaction, and we know when the enthalpy is positive and when it's negative. So thermite, when the thermite is ignited or heated by a chemical reaction, it releases a large amount of heat. Okay, there are very cool videos. You can search it on YouTube and see what happens. Just search thermite demo and you can see multiple videos. Okay, and what is thermite? Thermite is a mixture of aluminum and iron oxide, Fe2O3 solid. So that's a mixture of these two powders. So when you heat it a little bit to start the reaction, it gives off a lot of heat, and basically what happens is exchanging of the iron with aluminum. So you make aluminum oxide with elemental iron. So if you watch the video, you would see very hot red stuff dripping from the container, and that's basically it's molten iron. So the reaction gives off a lot of heat that can melt the iron. So you will see the iron, molten iron, just dripping from the container. So you can pause here and watch the video, search it in YouTube, or you can just answer it based on the information I gave you about thermite. So which of these four is true about the delta H sign and the type of reaction of thermite? Well, as we said, it gives off a lot of energy, a lot of heat, therefore it's definitely exothermic, right? It's not endothermic. It's giving off heat, so it's exothermic. So we just discussed this in the previous video. So when a reaction is giving off heat, right? So usually we have the reactants, and it's when it's giving off heat, so the products are in the lower state because it's giving off heat, right? So that would be the product, and it's giving off heat. Okay, so we have the H of product, H final, and here is the H initial. So if you have a lower value, minus, because we know delta H is H final or H of product minus H initial. So if you have a lower value minus a higher value, what would be the sign of the delta H? It would be a negative number, right? So it's lower than 0, it's negative number. So it's exothermic and delta H is negative. Therefore the answer is D. Okay, so now that we know what is enthalpy, and we talked about it a little bit, and we know what is exothermic and endothermic reaction. So let's go ahead and relate this to the chemical reaction that we've known in the previous videos, and related to the enthalpy. So when a reaction takes place in a constant pressure environments, the enthalpy change is synonymous with the heat exchange. Okay, so we've learned about enthalpy all the way through, and when we were talking about it, we were talking about giving off heat or absorbing heat. So we were saying heat a lot of time. Okay, so these two are going together all the way through. Okay, so heat and enthalpy. So when we have a constant pressure, the heat is exactly the enthalpy. And this is very easy to maintain, because in the atmospheric pressure is 1 atmosphere, and when you do a reaction in the atmospheric pressure, it's always constant pressure, and that's equal to the atmospheric pressure, which is 1 atmosphere. Okay, so it's easy to maintain this constant pressure, and it's easy to let's say calculate the amount of heat. We learned about that, right? So we had calculating heat and calculating work, so we know how to calculate the amount of heat. So the amount of heat which is absorbed or released by a reaction is the enthalpy of the reaction. So for reaction, again, I'm reading this again. For reactions that take place in a constant pressure environments, the enthalpy change, which is the delta H, is synonymous with the heat exchange, and we can calculate the heat exchange in a reaction. So I told you that we're going to go over the enthalpy definition, and then we're starting at thermochemical equations, right? So what is thermochemical equations? Thermochemical equation is just like the chemical equation that we've learned about, and it also have the amount of enthalpy change that happens in the chemical reaction. Okay, so it shows the enthalpy change as well as the mass relationship, just like the previous chemical equation we had. So this is thermochemical equation. In a thermochemical equation, we also have enthalpy. So here's an example. So H2O solid goes to H2O liquid. So this is not a chemical change, this is a physical change. And what is it called? It's just melting an ice cube, right? It's water solid, which is ice, go into the water liquid as water, and you see that we write the delta H right in front of it, right? So since the delta H is a positive value, is it an endothermic reaction or exothermic reaction? Well, it's S going from solid to liquid, right? It's ice to water. Ice require heat to change into water, right? So that's endothermic. Okay, so endothermic needs heat, require heat. And this, even with a sign, if you remember it, if we have a positive delta H, it means it's an endothermic reaction. Okay, so how can we interpret, like I'm trying to tie the things that we've learned for a reaction and apply it to a thermochemical reaction. Okay, so this reaction tells me that 1 mole of water, of ice, let's say, because it's water S solid, 1 mole of ice turns into 1 mole of water. Okay, and when we have thermochemical equation, we have the enthalpy. So the number that we see as a delta H represents the coefficient we have for anything we have in that reaction. Okay, so basically this means that for 1 mole of ice to melt into 1 mole of water, 6.01 kilojoule of heat is required, is absorbed. Okay, so that's how, let's say, we what's a good term for it, we read the thermochemical equation. We would say, if, for example, if this was 2, for example, then we would say for 2 moles of ice, we need this amount of energy. Okay, that's how we read the thermochemical equation. So the enthalpy is the amount of energy used for the coefficient number of moles. So the coefficient is telling you how many moles of that substance. Okay, so if we were just assuming 2, but here we have 1, so let's just cross out 2. So in this reaction, since we have 1 mole of 1 H2O solid, we would say 1 mole of water of ice, H2O solid of ice, require 6.01 kilojoule energy or heat to melt into water. So this is just a picture showing what we were talking about. This is the endothermic process because the process require heat. The heat is absorbed by the system from the surroundings. So H2O solid needs 6.01 kilojoule, and it's 1 mole of H2O solid require this amount of energy to turn into water. So this slide is a very important slide. So there are some things that you have to remember. Okay, when we have a thermochemical equation, the coefficients always refer to the number of moles of that substance. So as I was talking in our example, so 1 mole of ice need that amount of energy. Okay, so because the coefficient was 1, that 1 says 1 mole. Okay, so always the coefficient refers to the number of moles of that substance. The second one, so that was 1. The second one, reversing an equation. When you reverse an equation, the sign of delta H changes. Okay, so it changes the sign for delta H. For example, in our example of water, so we had H2O solid to H2O liquid, and we had delta H of positive 6.01 kilojoule, right? So if you reverse the equation, so if you say 1 mole of water, how much energy it needs to turn into 1 mole of ice. So we are reversing the equation. So when you reverse the equation, the delta H have a change of sign. So H2O liquid to H2O solid, now the delta H is negative 6.0801 kilojoule. Okay, so when you're reversing an equation, you have to change the sign of delta H. So that's the second important thing that you have to remember. The third one, so if we multiply both sides of equation, like for both reactant and product, by a number like n, we must also multiply the same number by the delta H. So if we say 2 H2O solid turns into 2 H2O liquid, what is the delta H? It's the same number multiplied by 2. Okay, and that makes sense, because right now we are saying 2 moles of solid, 2 moles of ice turns into 2 moles of water. It doesn't make sense if you say it takes 6.01 kilojoule, because now you double the amount of ice, so it needs double the amount of energy, right? So when you multiply a number by a reaction, both sides, reactant and product, you basically double the amount of energy. If you multiply it by 2, you double the amount of enthalpy as well. So you multiply the same number to the enthalpy. So that's the third one. So in the second one, we say if you flip the reaction, you change the sign of delta H. If you multiply the reaction by a number, you have to also multiply the same number by delta H. And the last one, number 4, equation must always specify the physical states of all the substance in the equation. So as you can see in this example, we always say solid, liquid, liquid, solid. We have gas phase, we have aqueous phase. So in a thermochemical equation, you always have to write the physical status. Not that for the other reaction we don't have to. Sometimes we don't, but for thermochemical reactions, because that is very important. Because if we don't write the phase here, just our example. So water turns into water, H2O turns into H2O. It doesn't make, there's no process, right? There is no reaction. However, this is not a chemical reaction, it's a physical change, physical process, but still, I mean, we have to write the phase for thermochemical reactions, because this change in the physical states require energy, okay? And that is very important. So the most common ones you would see solid, liquid, gas, and aqueous, but sometimes there might be some other forms, like for example for carbon you might see GR, or you might see the full term graphite, and or on the other hand you might see diamond. So that is also the phase of carbon, if it's in a graphite state or it's in diamond state, and that requires some energy to change, right? So for carbon sometimes you see these kind of physical state as well, but the most common ones are solid, liquid, and gas, and aqueous. Okay, so let's test what we've learned so far about the thermochemical equations in this example. So if we have this thermochemical equation, we have the reactants, we have the product, and you got the delta H, okay? What would be the delta H for this reaction? So you see that the difference between these two reactions, the product are now in the reactants, so it's flipped. Also, it is multiplied by 2, right? We have CO2 and 2H2. Here we have 2 CO2 and 4 H2O, or H2O and H2O. And also in the reactant side, which is now product. So it's all multiplied by 2. So it's flipped and multiplied by 2. So we say when we multiply a number by the reaction, you have to multiply it by the delta H2. And when you flip it, you change the sign, right? So we had negative 890.4 kilojoule. So it's doubled, so we have to multiply it by 2. Also, it's flipped, so we have to change the sign, so we have to make it positive, okay? So which is positive 1780.8 kilojoule. So therefore D is the answer. Okay, so we learned what is enthalpy. Enthalpy is the heat evolved in a reaction in a constant pressure. So the heat evolved in a constant pressure is enthalpy. We cannot define the exact amount of enthalpy as one state, but we can measure the change of enthalpy. And enthalpy is a state function, so we can find the difference by the delta H by subtracting the final minus initial. We also learn about thermochemical equations, which are just like the chemical equation that we've learned, it just have the enthalpy associated with it, the amount of energy, the amount of enthalpy change in that chemical reaction. And we learned some rules on thermochemical equations.